right, hey y'all, it's Mr. Kyle Myers Mathematics, and let's jump into it. On this one, normally I work it out from scratch and show you, even if I have to work it out beforehand. But this one was a little crazy, and I think there's probably also a solution that is a little more clean than the one I came up with. But I don't know, I was just having a brain fart on this one, on a cleaner solution than what I came up with. But let's go over it anyways, and I'll explain what you can see. Most everything you can see here in the image, my picture is just cutting off some simple math off to the side that I did. So number 62, consider a series combining geometric growth and arithmetic decrease. Let a sub 1 equal 1, or the first term is 1. Another way to say it. Fix a greater than 1 and 0 less than b less than a. So that would mean that b has to be positive, and it has to be at least, it can be less than 1, but it doesn't have to be. Because a can be like 1.000001 or something like that, and then b could be 1. They didn't specify that we had to be in a certain number system. So for countings, for in values, typically those are integers. But for actual a values, especially since we're talking about geometric, if you had geometric decay, we'd definitely be able to have fractions, even if you don't necessarily start off with fractions. So fractions and decimals are not out of the question, but if you're going to come up with your own values, I probably wouldn't, unless you just like to torture yourself, I guess. So 0 less than b less than a, b has to be at least positive, which means a has to be at least positive, but also a has to be greater than b. Okay, so we're setting a sub n plus 1 equal to a times a sub n minus b. So that is the recursive formula. So they're giving us the recursive formula, basically the way to get the next term from the previous term. And that's how we know that we have the geometric and the arithmetic. The a is the geometric, whatever a is, and then the b would be the arithmetic part. That's why we're subtracting it, because it's arithmetic decrease. So we're subtracting b, geometric growth. So a has to be positive, and a has to be greater than 1, because otherwise it wouldn't be a geometric growth. So that's why they're giving us those parameters. So it says find a formula for a sub n plus 1 in terms of a to the n power. That's the part that's actually kind of hard. At least I thought so. And a and b and a relationship between a and b such that a sub n converges. So if a is 2 and b is 1, let's start off with the last thing. The last thing actually is the thing I actually got the answer to first. Because when I first did this, I made a equal to 2 and b equal to 1, thinking, oh, well, let's just go with the simplest thing, right? If a has to be greater than 1, and I'm in the simplest number system, the natural numbers, then the next number would be 2. So let's just make a2. But if you make a2 and b1, you end up with a sequence that converges. It says a sub n converges. That's talking about the sequence. So if you're already starting to dabble in series, we're not there yet. This is still technically part of a set of questions that has to do with sequences, not series. A series is a sum of a sequence. So the sequence can converge, and I believe it converges, just to 1. It doesn't actually change at all. A sub 1 is 1. That we have to fix, or it has been fixed for us, I guess I should say. But if a is 2 and b is 1, and then a sub 1 is 1, it's just 1. It just keeps being 1. So, yeah. So that would be an a and b value such that a sub n converges for the last part. Then if you make a equal to 3 and b equal to 1, this is what happens. And I have this in the table. So one way I was trying to figure out what the pattern was is by looking at the table, seeing if there's some sort of easy pattern that I can come up with. Nothing really came to mind other than, of course, the recursive, which is built for us. So my recursive formula, if a is 3 and b is 1, would be a sub n plus 1 is equal to 3, a is 3, times a sub n minus 1. So if I do it that way, then I end up with 1, and then 2, and then 5, and then 14, and then 41, and then 122. After timesing by 3 and then subtracting 1. If we look at what's happening as we go, we are continuously timesing everything from the previous set by 3, which means that ultimately we want 3 to the power of n. So that's going to be this part. So ultimately we want 3 to the power of n minus, and then the next part's a little more tricky because you're continuously subtracting 1, but on the very next set, you times by 3. So you're taking that 1 and timesing it by 3, which then is subtracting 3. But then on the next set, you take all of that and times it by 3. So then that 3 gets times by 3. And then the next one becomes a 3. And then you subtract 1 from that. So it's literally 3 to the n minus 3 to the n minus 1 minus 3 to the n minus 2 minus, and you just keep going down until you get back down to 0, because ultimately at the very end of it all, at the tail end of your recursive is always a minus 1. So a simpler way just came to mind. You could just do the sum starting from k equals 0 of 3 to the k power, and then do n minus 1 instead of n minus 2. And I think that actually would be a simpler way to do it. So that would mean, for instance, that it wouldn't work really well for n values. Well, starting from 0 going to 0 would just be 1, because then you're not inputting anything into the summation. So actually, I think that would work pretty well. So the sum from k equals 0 to n minus 1 of 3 to the k power, I think that would work actually. Because then on the, oh, no, it wouldn't. No, we do need the minus, because the very, very first term doesn't get subtracted, but every term after that does. So yeah, we did need that summation. I was trying to think of how to consolidate it, even doing this live here. But yeah, that very first term is the only term that isn't negative. Every other one is, because every other time other than the very first time, we're subtracting something, and then timesing that subtraction by 3, and so on and so on. So this is about as clean as it gets. 3 to the n minus, and then plug all this in here. So for instance, if this doesn't work for the first few terms, but it works for the terms after that, because it's n minus 2, right? So like it would only start to work for values of n starting at 2. Before that, it wouldn't work, because it just doesn't work to plug in a summation that goes from k equals 0 to a negative number. I mean, you can't do a summation from 0 to a negative 1. That doesn't work that way. So yeah, so this is about as clean as I could come up with. If you're watching this and you are a math extraordinaire and you came up with a cleaner solution, let me know. Just nothing came to mind when I was building this. So yeah, I played around with some other options here, trying to try out some other things, like 30 to the n minus 1 minus 3n minus 5. Just playing around with different options. I was doing a bunch of different things, and I was just erasing them and then rewriting them. So this was the last attempt I made before I was like, you know what, I'm just going to go with 3 to the n minus the sum of k equals 0 to n minus 2 of 3 to the k. So that's the formula for a sub n plus 1 in terms of a to the n power. So that's the very first part, the part that I said was going to be the hardest, writing it in terms of a sub n. And then you have a and b in a relationship between a and b such that a sub n converges. That we already talked about at the very beginning. That would be if a is 2 and b is 1. Okay. So yeah, that covers everything. Again, if you found a cleaner solution, let me know. You can drop that in the comments below, or you can shoot me an email. My email is on my website, myersmathematics.com. You can go check that out. I'll have that in the description down below. And you can check out some of my resources. I have, free resources that are on my website, as well as paid ones, because I do math tutoring, and I also make content especially for Calculus 2, since I tend to have a lot of students that are requesting Calc 2. So I made a whole course for Calc 2. You can go check that out as well. And all of that is at Myers Mathematics. I'll catch you in the next video. Blessings, y'all.